Talking about the marine environment, we know that these extreme, the climate change and climate modes of variations are affecting marine heat waves, fish mortality, and the coastal hazards, especially storm surges, and which are going to be more intense and more frequent in global warming scenario, are going to cause a lot of hazards to the coastal regions. And we all know that most of our mega cities are based on the sea. So they are very coastal, and the sea level rise and coastal hazards are going to affect a lot our society. So when we discuss these extremes and their impact on our society, naturally our implication goes to climate change. But climate change is at the end of this chain of processes. We have many, many processes in atmosphere and ocean atmospheres. So starting from wild wind, tornado, which lasts for only 1 hour or so, and very, very small scale, 50 to 100 kilometers. Then you have the cyclones, the Madden-Junial oscillations, the interseasonal oscillations, and then the El Nino and IOD. So these are kind of chain of processes which are embedded in that climate change, which happens once in like 100 years, 200 years. There are, of course, natural climate change and also anthropogenic climate change. I'll come to that later. But there are several processes which are also embedded in this kind of gradual shift towards a warming world. So we should not neglect those kind of variations which are happening from time scale of hours to seasons. Because without knowing them, it will be very difficult for us to understand how climate change is going to influence us. Climate change is just a secular trend. It's just a rising of temperature. But on that rising trend, we have these kind of variations which might become more intense and more frequent, and that's what we want to study. So I'll focus more on those kind of processes and try to link them to the climate change and try to say what we may expect in the future. This is atmospheric physics. Maybe some of you may be knowing that we have just like 30 kilometers of the atmosphere, which is kind of controlling everything in the world. And why we are interested in that? Because in physics, you can measure, you can estimate the temperature of any planet, any satellite, not only in our planetary system, but anywhere else in the galaxy or outer galaxies. And that is based on a simple rule given by Stephen Boltzmann. By that rule, if you apply that rule, what is the albedo, what is the incoming radiation and outgoing radiation, you can easily calculate what will be the temperature of any planet. So for the Earth, the temperature is 255 Kelvin, which is minus 18 degrees centigrade. So that is the black body temperature. If there is no atmosphere, that will be the temperature of the Earth. No atmosphere, no ocean, then the temperature of the Earth will be minus 15 degrees centigrade. So in some sense, we are lucky that we have fluid in our system, the water and the atmosphere, which is changing and that kind of black body temperature to like comfortable temperature like plus 15 degrees centigrade, which is comfortable enough, global average plus 15 degrees centigrade, which is comfortable enough for us to survive. There is another way to also calculate in a simpler way. You can put that into a simpler T temperature is equal to Stephen Boltzmann constant divided by sigma and take a 1/4 root of that, then also we'll reach the same temperature. So that's why it is very important to understand the atmosphere and ocean of the system to actually estimate the real temperature of that planet or that satellite. For that example, I have given here the Titan temperature. Titan temperature is expected to be minus 191 degrees centigrade if you just take the black body radiation equation. But actually the temperature is higher than that, mainly because Titan and other planets of Jupiter, they have fluids, not necessarily atmosphere like us, but they have fluids. That's why the temperature is higher. So the atmosphere is very important for us, the ocean is very important for us, and the radiation budget which is happening because of this atmosphere and the gases, aerosols we have, the balance is something like that. So if you are getting 100% radiation coming from sun, 30% is reflected back by the clouds and also the snow and land surface. 51% is absorbed, 19% is absorbed by the atmosphere, and 51% is coming to the earth, ground, and the oceans. From that 51%, 7% is going back as sensible heat, 23% is going back to the atmosphere as latent heat, and 21% is going back to the atmosphere as long wave radiation. Because Earth is a black body, so it is also radiating back the radiations. So 21% of sun's radiation coming to the earth is actually radiated back as long waves. So you can see that 100% coming in from sun and 100% going out of the sun. So then how we maintain our temperature? If the radiation incoming is equal to outgoing, then the temperature should be 0, right? Why we have 15 degrees centigrade average? Now it's going towards 17 degrees. So why you have that temperature? Because we are converting solar radiation into 3 different kind of heats. Sensible heat, which is kind of convection, and latent heat, conduction. Latent heat is convection. And then the long wave radiation. So that conversion from short wave radiation, which we are getting from sun, and to these kind of 3 radiation, sensible heat, latent heat, and the outgoing long wave radiations, which are less intense compared to this short wave we are receiving. So that conversion from short wave to long wave actually is giving us enough energy to maintain the 15 degrees centigrade balance. So you can see that we have a very, very delicate balance. Slight change in this will cause problem, and that's what we are expecting now. Because we are increasing greenhouse gases, the solar radiation which is going out of our system are not going as much as it used to be. So some energy which was going out of our system as long waves are absorbed by the atmosphere and radiated back to the earth. So that's what is increasing our heat. I'll come to that later. The other aspect is the climate we are expecting, we are actually experiencing, is because of the tilt in Earth's axis. The 23.5 degrees tilt actually is exposing one part of the Earth in one season compared to the other season. So that's why we have summer season where the northern hemisphere is more exposed to the sun. In June, July, August, summer season for the northern hemisphere when the Earth northern part is exposed to the sun. Similarly, for the December, January, February, the southern hemisphere summer, the southern part is exposed to the sun. And in between, you have the 2 equinoxes. So that's how our seasonal system is running, and that's why we are experiencing this kind of shift in the sea surface temperature to the northern hemisphere during June, July, August, and the below plot here, the plot here. And the winter time when it is coming to the south, so you can see more warmer temperature coming to our southern hemisphere during December, January, February. And that's what is maintaining our climate system, and that's how we are experiencing our climate system. Now there is another thing in this plot, if you are careful. So if you are careful, you will see that one thing is that there is a shift in the temperature from north to south depending on which hemisphere is exposed more to the sun. In June, July, August, northern hemisphere is exposed more, so the higher temperature you can see even coming to the northern mid-latitude of Pacific Ocean. Similarly, in December, January, February, the higher temperature you can see even southern part of the subtropical South Pacific. Besides that, we also see cooler temperature, east-west gradient. The western part of Pacific is warmer than the eastern part. Similarly, you can see that western part of the Atlantic is warmer than the eastern part. So the African coast, western African coast there is cooler compared to the Mexican coast here. And similarly, the California coast is cooler compared to the Philippines and Indonesia here. So why this part is warm compared to the eastern part, although both sides are receiving same amount of sun's energy. Okay, in June, July, August, or December, January, February, depending on the sun's altitude, we can expect which part of the latitude will get the amount of energy. And for one latitude, the energy is same, whether western part or the eastern part. So why we are getting this kind of cooling on the eastern side of the ocean basins? Those who have done already physical oceanography already know that, why it is happening. Mainly because we have the trade winds. The wind system is helping us for the coastal upwelling. Like the winds, when they blow from south to north to south in northern hemisphere, will transport water away from the coast. So that's why subsurface water will come in, and that upwelling will cool the system. That's why the eastern side of the basins are cooler in Pacific and Atlantic. Indian Ocean is slightly different because we have the monsoon system. So that's why, depending on which part of the monsoon we are, southwest monsoon, the Somali coast is cool, northeast monsoon, the Sumatra coast is cool. So depending on the monsoon, Indian Ocean experiences the upwelling. But the other two basins, Pacific and Atlantic, they are experiencing throughout the year upwelling on the eastern side. And that's how the climate is actually managed by that system. If you don't have upwelling, we will not have El Nino. Some of the years when the upwelling is weak, that's the year we get the El Ninos. Some of the year when the upwelling is strong, we get the La Nina, like this year. So that's how our climate system is maintained by that upwelling system, and it's very important for physical oceanography as well as marine biology, these upwelling systems, because they help fishery and ecosystem through upwelling of nutrients besides upwelling of cold water. Okay, so coming back to climate change, we saw that 235 watts per meter square is coming in, and 235 watts per meter square is going out, and we are maintaining the temperature because of the conversion of short wave radiation to long wave radiation. That's fine. But what's happening now is we are kind of increasing the greenhouse gases, which is absorbing more long wave radiations. Like greenhouse gases, carbon dioxide, methane, and some other gases, they allow short wave radiations to come in, but they don't allow the Earth's radiation, long wave radiation, to go away. So they're trapping some of the long wave radiation, and that's how the temperature is increasing for the Earth. And this is the proportion of the heat or the radiation we are expecting because of those greenhouse gases. Carbon dioxide is the major culprit. It is giving like plus 1.5 watts per meter square. If the Earth is sensitive enough, that will be converted into 1.5 degrees centigrade temperature rise. Okay? And similarly, methane is the next one, which is giving us 0.5 watts per meter square. Because we have methane in the atmosphere, it is trapping 0.5 watts per meter square. So if the Earth is sensitive enough, that means the methane will contribute to 0.5 degrees centigrade rise in the global temperature. And the next one is chlorofluorocarbons, CFCs. It's reducing now because of societal pressure. But that is contributing like 0.35 watts per meter square, which is equivalent to, again, 0.35 degrees centigrade rise. And the next one is nitrous oxide, 0.15 watts per meter square. So together they are contributing like 1.552, and then this is 0.5, so 2.5 watts per meter square, which means 2.5 degrees centigrade rise in the temperature. So that 2.5 watts per meter square, which is coming to the Earth and increasing our temperature, actually that excess heat is helping the global temperature to go on. And now if you compare to 1860s, we are kind of 1.5 degrees centigrade warmer than what it used to be in 1860s. So that 2.5 watts per meter square on average, which is happening because of greenhouse gases, is actually has contributed already a rise of 1.5, 1.6 degrees centigrade global temperature.